Today we're going to look at a conical pendulum question. A conical pendulum is a mass moving in a horizontal circle suspended on a string, as you can see here, which moves in a circular path at a constant speed. And as it does, it sweeps out a three-dimensional shape equivalent to an upside down cone, hence the term conical pendulum. Now this particular question gives us three pieces of information. It gives us the mass, or the size of the mass in kilograms, 4 kilograms, the radius of the circle, 0.38 meters, and the speed at which the mass is moving, which is constant. Notice that the speed is constant but not the velocity. Since the mass is constantly changing direction, the velocity is changing in its directional component. And therefore, since the velocity is not constant, the mass is accelerating. But it's a kind of acceleration that does not involve speed change, rather it involves direction change. And this is true of all circular motion, that the direction change involves an acceleration towards the center. And we call this a centripetal or center-seeking acceleration. We'll talk more about this as we proceed through the question. Now the question asks three things. Let's read it first. A 4 kilogram mass suspended from a light, inextensible string moves in a horizontal circular path of radius 0.38 meters with a constant speed of 2.5 meters per second as shown below. Notice that we say a light string, since the mass of the string could affect the motion if it was significant. So by saying light, we're making the mass so small that it can be ignored. And the word inextensible means constant length, again, so that the motion is not affected by a complex bouncing which could occur if the string was able to change length. The first part of the question asks us to calculate the angle theta which the string makes to the vertical. Shown up here, we can see that this is the angle from the string to the vertical. Now, I may just stop this rotating mass so that we can focus on its stationary position in order to label the question. So we'll just stop this here on the left side, and keep in mind that we'll be annotating or labeling the mass on the right side so that we can calculate values of different things required. Now this angle between the string and the vertical is sometimes referred to as the semi-vertical angle. The full vertical angle would be the angle between the string on one extreme to the string on the other side, and you can see that it is half of that angle, hence the term semi-vertical angle. The second part of the question asks us to calculate the magnitude of the tension force in the string. The tension force will be acting upwards on the mass in a direction parallel to the string. Of course, because it's moving and force being a vector quantity, then the force will be changing direction constantly. And we're not going to complicate the question by trying to consider that, so we're just going to ask to calculate the size of this force. That's why we use the word magnitude, which means size. Part C, the period of revolution of the mass. Period is the time taken for one complete cycle, or in this case, one 360-degree rotation. Let's look at part A of the question, that is, calculate the semi-vertical angle theta. Now in order to do this, we need to identify and label all the forces acting on the mass in question. And there will be two of them. The tension force previously mentioned, and of course a weight force acting downwards. So let's label all the forces acting on the 4 kilogram mass. Since we know tension is involved, we'll let T represent the tension force, and we'll show this in yellow, acting parallel to the mass. There we have it. And the second force that I mentioned earlier was the weight force, so we'll represent that with the letter W, and we'll show that in red as an arrow acting vertically downwards. Over here, acting vertically downwards. Now in order to work with these forces, we're going to need to resolve them into directions which are both either parallel or perpendicular to the motion. In this case, the weight force is already perpendicular to the motion, and the tension force is not. So we will break the tension force into two components. That is, a component which acts either vertically, which will be perpendicular to the motion, just like the weight force, and horizontally, which is also perpendicular to the motion. There's no component of force acting parallel to the motion at any time, since if there were, that would cause the speed to change, and we know it's a constant speed. So, breaking the tension into these two components, and we've represented them with dashed arrows, we can effectively replace the tension force with these two components, which would have the same effect as a vector sum would add to the diagonal component, but these two together would have the same effect on the mass as the single tension force shown as a solid line. And so that's the whole idea of resolving a force into components. We're replacing it with an equivalent set of forces which have the same effect but are easier to calculate with. So, the first or vertical component of this tension force will be given by t cos theta, since we might note that this angle theta, the semi-vertical angle, is equivalent to the angle over here between tension and a vertical line. Of course, the verticals on both sides are parallel, and this is like a traversal in that is a line crossing two parallel lines, and that makes these two angles alternate angles from your high school geometry, although you don't need to use that terminology. We just need to identify that these two angles are the same, and you can see that anyway. The other component that we need to label is equivalent to the side opposite this right angle triangle, and therefore we would label that as t sine theta. Now that we've identified both the vertical component, t cos theta, and the horizontal component, t sine theta, we can look at this in a bit more detail. And here's where it gets interesting. Since the mass is travelling in a horizontal circle, at no stage does it accelerate vertically. This means that any vertical forces acting on the mass must be in balance. That is, the t cos theta upwards must balance the weight force downwards. So that's our first equation. Vertically, the forces must balance, therefore t cos theta equals the weight, which we know is equal to mass times gravitational field strength. Now we don't know theta, and we don't know tension, and so therefore we can't solve this equation straight away, and whenever that happens in any maths or science question, it's a good practice to label the equation with a number that is a reference that we can come back to use later on. So now let's look at the other component of tension, and it's the only part of the force that is not cancelled out. T cos theta balances the weight. They're cancelled out. So the only part of the force left is t sine theta, and therefore that must represent the net force. Horizontally, the net force provides the centripetal force, that is the center-seeking force needed to act radially inwards and cause the mass to travel in a circle. So we can write t sine theta over here, acting radially inwards, must equal the net force represented by sigma f, sigma meaning sum. And since the motion is circular with a constant speed, the net force must in size equal this expression here, mass times speed squared divided by radius of circular path. Now, we haven't derived this. You're expected to know this expression for the size of the net force for circular motion. We could derive this in a later video. So this gives us our second equation. Again, two unknowns, t and theta. Mass, speed, and radius are given. So we've got two equations in two unknowns, and this means simultaneous equations. The best way to solve this is to divide equation 2 by 1, and this achieves two things in one action. Dividing equation 2 by equation 1, so equation 2 is t sine theta equals mv squared over r, that's this expression here, and equation 1 is t cos theta equals mg, shown on the bottom. Now you might notice straight away that the t's cancel off, but also the masses cancel off, and we eliminate two of the unknowns straight away. or two of the variables straight away. We do know the mass. It doesn't matter though, since it cancels off. And when we cancel these off, t sine theta over t cos theta becomes tan theta, sine over cos being equivalent to tan. So we end up with tan theta equals v squared over r, and the g can come up here. The masses having cancelled leaves us with tan theta equals speed squared over radius times gravitational field strength. We know the speed, we know the radius, we're allowed to assume the value for gravitational field strength as either 9.8 or 10. The actual value at the equator is 9.80665 newtons per kilogram, but many physics courses round this off to 9.8 or 10, and the trend lately has been to round it off to 10, so I'll do that, even though I'm not a big fan of rounding it to 10, since it implies that it's some sort of decimal value which is not correct. On different planets it's completely different. On the Moon it's around 1.6, on Mars it's around 3.4, on the Sun it's around, not that you'd stand on the surface of the Sun, it's around 86. Okay, so substituting these in, we get 2.5 for the speed squared, 0.38 for the radius, and g equals 10 newtons per kilogram rounded off. This gives us to 4 decimal places, 1.6447, which can be inversed to give us the angle to the nearest degree of 58.7 degrees. Now that's by far the most complex part of this whole series of questions, calculating the semi-vertical angle. Since now we have the semi-vertical angle, we can substitute it into either equation 1 or 2 to solve for the tension, and that's how we do part B, calculating the magnitude of the tension. Part B, calculate tension. Now I've selected equation 1. Equation 1 is a simpler looking equation than equation 2, however they would both work. T cos theta equals mg, I'm just writing it down again without having done anything, so that we've got it there as a reference. It's always good practice when you're showing your working to do that. Now we can substitute in the angle, 58.7 degrees, the mass 4 times the gravitational field strength, again we're using 10. This gives us t times 0.5195 equals 40. Dividing both sides by 0.5195 gives us pretty close to 77 newtons precisely. So rounded off to 1 decimal place at 77.0 newtons. Now you might notice that's the size of this tension force, so the horizontal component would be significantly less than that, and that would be the size of the net force. Had the question asked to calculate the net force, we would then multiply this by sine of 58.7, although we could have done it directly using mv squared over r, for which we already have all the values. Part C asks us to calculate the period of revolution, that is the time taken for one rotation. Now we don't need to use any of this information that we've already got to calculate the period, since we can simply use the fact that the speed at which the mass is moving is equal to the distance that it travels divided by the time, and the time is the period for one circle. So using the old simple equation, speed equals distance over time, the distance being the circumference of the circle and the time being the period that we're required to calculate, and the speed being given to us as 2.5. So we substitute in the circumference 2 pi r, again we know the radius, so that's easy to calculate, and we're after the period, which is often represented by a capital T, but notice not the same as the tension, which is a straight-edged T. The period normally has these two little notches on the side to distinguish it from tension force. Although it is visually very close to the tension symbol, be careful not to confuse the two pronumerals. So T with the two notches, period, equals 2 pi r over v, having switched the v and the t there. 2 times pi to, I've used more decimal places than we probably need, but you can just bring up pi on your calculator as a more precise value, times the radius 0.38 divided by 2.5 gives us just under 1 second, or 0.95 seconds. Now, On this animation, you may have noticed that it took a lot more than 1 second to do a lap. It was more like 3.5 seconds. So this is just an animation to show the circular motion. The key things to remember here are we resolve forces into two components. We cancel them vertically, or equate the two forces vertically, and the horizontal component of tension provides the necessary centripetal force to make this mass travel in a circle. And this gives us two equations which are solvable. Again, if you had been asked to calculate the net force, we simply would have used mv squared over r is net force, and we could have done that straight away with the three values already given in the question. Hopefully this has been useful to you. If you like, you can check out my other YouTube channels. Of course, Ask Mr. Physics is this YouTube channel. Ask Mr. Maths is my other one. So feel free to use those, and again, I will answer any question that you pose in the comments. If you found this video useful, please like it and please subscribe. I'll see you next time. Thank you.